Welcome to Study Loop.
We're told we wanted to take a nice hot bath, but discovered that our roommate has used up most of the hot water. Um, we filled the tub with 270 kilograms of 30 degrees Celsius water and attempt to warm it further by pouring in 5 kilograms of boiling water from the stove. So here is our bathtub. We have our existing water in here at 30 degrees C. We pour some hot water in to try to warm this up. And we are given all these things. And then we also know that the total mass of water in the end after we pour it in is just the sum of the mass of the hot and the cold waters. So we're asked if this is a reversible or irreversible process. Well, pouring hot water into the cold water is an irreversible process. And you can think of that as there's no way of then extracting the hot water from the cold water without doing some additional work. Such as you could do it, I suppose, if you had some thermal process, heat pump that would take heat from the water and then warm some other water. But there's basically no way of, once you've mixed the waters, there's no way of going back and unmixing them. So then it asks us to calculate the final temperature of the bath water. Well, we can do that by knowing that the change in internal energy of the hot water must equal the change in internal energy of the cold water. And so the change in internal energy of the hot water equals the mass of the hot water times the heat capacity times the change in temperature of that hot water. So it's initially at 100 degrees C, and the final temperature is what we're trying to determine. So we have the change in internal energy of the cold water is the mass of the cold water times the heat capacity times the temperature in the cold water minus the final temperature that we're trying to determine. So we equate those two things, and we get that the equation here, and we get that the heat capacities cancel out. And if we rearrange some things, we find that we have the final temperature, and this is the total mass, equals the mass of the cold water times the temperature of the cold water plus the mass of the hot water times the temperature of the hot water. Now, if we solve for the final temperature, we see that actually it's a mass-weighted average of the two temperatures. So we get the mass of the cold times the temperature of the cold divided by the mass of the total, plus the mass of the hot times the temperature of the hot divided by the mass of the total. And plugging those numbers in, we get 304.43 Kelvin. Which is not a whole lot warmer than 30 degrees Celsius. So we didn't warm the water up a whole lot, and we're still going to have a miserable bath. Now, to find the change in entropy, which is what we're asked for next, assuming that there's no heat exchange with the air or the tub itself. Well, to do that, we need to take a look at how the change in internal energy, how that changes with temperature. Right? So the change in internal energy of the hot water is the mass of the hot water times the heat capacity of the hot water times the temperature that it's at minus the temperature it was initially. And we can then write our entropy statement in differential form. So that is and the problem is here is that the heat is not being dumped at a certain temperature, because the water and the both water, the hot and the cold, are changing temperature as they exchange heat. So we need to do an integral, and that integral we can find because we know the differential of the entropy equals the differential of the internal energy divided by temperature. And so if we integrate this, we get the change in entropy equals the integral of the differential of the internal energy divided by T, and we can write that as the integral of 1 over the temperature times the derivative of the internal energy with respect to the temperature times dt. So we get an integral in terms of temperature, in terms of dt. And if we plug that stuff in, okay, so now we need to figure out what du dt is. Okay, so for the hot water, we have this u as a function of t, so we can take the derivative with respect to t, and we get du dt equals the mass of the hot water times the heat capacity. So that means that the change in entropy of the hot water is the integral from the initial state, the initial temperature, to the final temperature of 1 over T times the mass of the hot water times the heat capacity. That actually comes out of the integral, so we get an integral of 1 over T dt. And if you remember from calculus, that is the natural log. So we get that the mass of the hot water times the heat capacity of hot water times the natural log of the final temperature minus the natural log of the initial temperature. And using our properties of the logarithm, we can get that is the mass of the hot water times the heat capacity times the natural log of the temperature ratio of the final temperature divided by the initial temperature. And if we plug in numbers, we have everything here, so we can plug in numbers and we get minus 4,265 joules per Kelvin. So that's the change in entropy of the hot water. So its entropy went down. Now we need to figure out the change in entropy of the cold water, and we can go through the same process, and we get its change in entropy is its mass of the cold water times the heat capacity of water times the natural log of the final temperature divided by the initial temperature. And plugging in numbers there, we get that is 4,739.5 joules per Kelvin. So the entropy of the cold water went up, which we'd expect, because we better get a net positive number for the change in entropy of the system. And if we take 4,739.5 minus 4,265, we get that the total change in entropy of the system is 475 joules per Kelvin.